Hello everyone, I am Soumya Ma'am, Assistant Professor of Civil Engineering at Vedang Institute of Technology. Today in this class, we will discuss how to analyze a structure. Whenever we analyze a structure, we just do the prediction. What amount of load it can take, what amount the deformation it will have, and how a structure will behave under some specific load and some conditions. So, the primary goal is to determine what the internal forces, and from the internal force we can find out shear, bending moment and axial forces, also the deformation. From deformation we will get how much deflection of the structure is going to happen and what amount of rotation it will happen. So, in our previous class we have discussed whether a structure is determinate or indeterminate one. So, now there are some examples of determinate and indeterminate structure. So, before analyzing the structure, we can analyze a determinate structure from equation of equilibrium. We know the equation of equilibrium and from that we can analyze the structure. But to analyze an indeterminate structure, we require some different kind of methods, or you can say the compatible methods. So, an indeterminate structure is a structure where the unknown reaction or internal forces are more as compared to the equations of what? Equilibrium. So, equilibrium alone is not enough to finding out or to analyze the indeterminate structure. For that, we will require some compatibility or deformation of material. So, some determinate structures like simple supported beam, cantilever beam, perfect truss. But always we cannot have simple supported cantilever and truss. So, for some beam like fixed beam, continuous beam, or you can say fixed frame, redundant truss, prop cantilever, we need to use some different methods. So, today in this class, we will solve some numericals using force method, or you can say flexible method, that is method of consistent deformation. This is also called as force method or flexible method. This method of consistent deformation we can use by using some slope and deflection formulas. To continue the process, we need what? Some slope deflection formulas. In this method of consistent deformation, we will use some procedure step by step. Let's go for it. Like here, the method of consistent deformation, also called as I said already, the force method and flexibility method. It is used to analyze what? The statically indeterminate structure. So, how to know determinate or indeterminate? In our previous class, I have already discussed. So, the structure must be like beam, frame and truss. Let's go for the procedure to solve what? Method of consistency deformation. In case of method of consistency deformation method, first thing we need to what? Draw the structure. Then we'll go for determining the degree of static indeterminacy. First, we will find out how many extra unknown reactions or internal forces exist. So, what are the number of extra force or extra unknown we have? From that, we will find out what? The degree of indeterminacy, that is equals to E of DES. Okay. So, in first step, we will find out DS. So, DS is what? DES is your DSE plus DSI, like degree of static indeterminacy external and internal. So sometimes for beam we take this as 0 and we will calculate DSE. In our next step, we will find out a redundant force or reaction. So when we solve the numerical, let's go for a numerical first. Suppose we have a propped cantilever beam. Okay. Suppose we have a propped cantilever beam. So in here you can see we have one moment, we have an reaction here and a horizontal reaction also. Okay, here this is of 3. In case of prop cantilever, here we will have one roller support. Okay, no issue. So sometimes we consider this horizontal as, or we can neglect this, because in case of beam we generally doesn't consider the horizontal force. So what we will do, here we will take the reaction as 2 and for roller we will consider the reaction as 1. So total reaction here you will have 3. In case of beam, for the we will take what? The general static equation. So here the equation will be summation of all the forces in vertical direction is equals to 0 and summation of all the moment equals to 0. We will only consider these two equations. So here the number of equation is what? 2 and unknown is 3. So unknown minus equation is equals to 1. So these become the number of redundant force. When solving the question, we will go in detail. Okay. So next step, we will analyze the primary structure for external load. Whatever the external load we will have, we will analyze the structure on basis of that. In next case, we will analyze the structure in case of using the redundant force. And after that, we will go for analysis. Let's go for one example. What? Analysis of structure. What kind of structure? Analysis of indeterminate structure. Okay. So indeterminate structure, to analyze the indeterminate structure, first thing we will draw indeterminate beam. Here I have taken one propped cantilever beam. Okay. So in case of propped cantilever, we will have a fixed support at one end and a roller support at another end. So the loading condition here will be UDL. Let it be W kilonewton per meter. And the beam must be AB and let's the span is L. Here this is the question and we will solve this. So first we will go for the step 1. In case of step 1, we will go for finding out DS. As here you can see here the number of reaction at fixed end is 3 and at roller is 1. But generally we will neglect the horizontal one. So I can write the unknowns here is equals to 3 and the number of equation is equals to 2. From this we will get what? DSE as 1. But we know that DS, your degree of indeterminacy, is equals to DSE plus DSI. What are this? This is degree of indeterminacy this DSE as external degree of indeterminacy and DSI as internal degree of indeterminacy. Okay. So, in general, we do consider this as 0. So, now your DSE is, sorry, what? 1. So, what is making the all the problem? This 1. Next, we will go for the step 2. In step 2, what we will do? Finding out the redundant. Let's draw the structure. So, always redundant must be your reaction. Okay. And here you have one reaction. So, if we just cancel this reaction, the structure will become unstable. So, it is easy to make this one as redundant. So, what we will do? Let's cut this. So, we will make the structure look like this with having one rotation and one vertical reaction, that is RA and MA. So, now we just cancel this redundant as per what? Here you have the step 2. Select redundant force or reaction. Choose one or more redundant. As we need one redundant, so we have cancelled the roller support one and remove them. After removal, the structure become statically determinate. Let's check whether the structure becomes statically determinate or not. So here you can see, as here 2 reactions are there. So the structure is already statically determinate. Okay. Now we will do what? We will just cancel the redundant force. Now we will go for what? Check here. Analyze primary structure for external load. Then we will apply unit redundant force. Now we have deducted the redundant force. We will analyze the structure with external force. Here the external force is W kilonewton per meter. So when the structure is like this, it will become, after applying load, it will look like this here A and B. So this deflection, let's name it as delta B1. Okay, so this delta B1 will be WL to the power 4 8 divided by 8 EI. Make it a box. Okay. So after cancelling the redundant force and analyzing the structure with the external load, that is UDL, we will have the deflection as delta B1. So whenever we have redundant as force, we will find out delta. If we have the redundant as movement, okay, if we have force, we will find out delta. If we have the movement as redundant, we need to find out the theta. Okay. So the first analysis is done after calculating this with external load delta B1 as WL to the power 4 upon 8 EI. So now the step 4 will be, we will cancel the external load and we will put the redundant. As the direction change, here the deflection also will change. Can see here? This will become like this. So this deflection, let's name it as delta B2. And the delta B2 is going to be your RB, WL cube, sorry, not W, RB L cube upon 3 EI. Okay. So here we have completed the step 3 and step 4. Now by using the equation of equilibrium, we will get for what? We have the delta B1 as WL to the power 4 upon 8 EI and the delta B2 as what? RB L cube upon 3 EI. So if we go for finding out the whole deflection, so this delta B will become delta B1 plus delta B2. Okay. Here you can see, if we have that this RA plus RB, that will be a WL. How? By equation of equilibrium. You can see all the vertical direction, the summation of all the vertical direction forces acting in vertical direction must be equals to 0. And we will go for here now. Let's go for delta B first. WL to the power 4 upon 8 EI. So this RB will take as minus sign. Why? Here you can see the changing of sign. Minus RB upon L cube divided by 3 EI equals to 0. RB, okay, cancel this cancel. Now we have RB upon 3 as W by 8 WL by 8. So RB will be 3 WL upon 8. Okay, just see the calculation. Okay, so now we got the value of redundant. Okay, what is the redundant value? We got now. Now we will go for the calculation of array. As we are analyzing, we need the reaction at A, we need the reaction at B. So RA will get from here, RA plus RB is equals to, here you can see the load applied here is W kilonewton per meter. W is acting along the beam. So the load will be WL. Okay. Now this RA is equals to WL minus 3WL upon 8. RA equals to 8WL minus 3WL upon 8. RA will be 5WL upon 8. So we have another reaction here. Now we will go for calculation of moment at point A. Let's make the structure as RA equals to 5WL by 8 and RB equals to 3WL upon 8. And what will be the moment at point A? So we will go for MA as RB into L minus W into L square by 2. And the moment at A will be 3WL into L upon 8 minus WL square by 2 . 3WL square minus WL 4WL square, that is WL square upon 8 in minus. So here I have changed the sign, plus as minus. Okay. As we are considering RB from right side, the sign will be negative here and here is the UDL. So UDL in from upward direction, from downward direction. So it will be WL square upon 2. Now here the MA is WL square upon 8. When we are saying that analyzing a structure, that means finding out what? Bending moment diagram. To find out bending moment diagram, we need to get bending moment at a certain distance like at xx. So here I have taken a section xs at x distance from RA, or you can say from left. Okay. So if we go for movement at xx, that will be what? This RA multiply with x minus movement, you can see anticlockwise rotation. So movement will be negative MA and minus WX square upon 2. Okay. So this movement at xx, you have to write like movement at xx section from left. Okay. So now we will put the value of RA and MA. This RA is equals to 5WL upon 8 into x minus MA as WL square upon 8 minus WX square by 2. Moment at xx. Okay. Now what to do? Now we will do find out the value of x. To find out x, what we need? We need the formula for maxima and minima. So we'll go for derivative of movement at xx, that will be derivative of here 5WL upon 8 into x minus derivative of here movement at, this is MA. So here you can see the this is the constant, no x is here, so we will take it directly as 0. Minus 0 minus this WX square by 2, W by 2 is your constant, for x square we will have 2x. Okay. So this is will be 5WL upon 8 minus W by 2 into 2, cancel. So 5WL upon 8 minus W I can write here that 5WL upon 8 will be W, so W will be cancelled. This is going to be your 8 as x. Okay. So here your x value will be 5L upon 8. Okay. Yes. Now, what we will do? Here, in this formula or mxx, we will put the value of x. Let's go for it. That is 5WL upon 8 multiply with 5L upon 8 minus 0 minus WL square by 8 minus W by 2 into x square, that is 5L by 8 whole square. After solving, we will get the value as okay. You have to calculate this. So, after calculation, we will get the value as 9WL square upon 128. So, this is the value for bending moment at maximum. Okay. We have already the bending moment at value A. Let's go for the bending moment diagram. Bending moment diagram of what? Of beam AB. We know that we have the loading condition as UDL. For UDL, in case of bending moment diagram, we have to draw the structure as parabolic. We know that. So, in case of AB, moment at A will be in, it will go below the structure, and here moment at A is, here you can see WL square upon 8. So, it will be moving in downward direction. So, now this will look like, and this point is your bending moment at maximum, that is 9W L square upon 128, and here the distance x. So, when the bending moment diagram is crossing this beam, that is known as your point of contraflexure. Okay. So, this point of contraflexure we will take another class to solve that. To solve a method of consistent deformation, first thing we have get the RB value here. The first thing we need to do is finding out the redundant force. Then we can put the equilibrium equation and we will get the rest of the values. So, in this class we have solved a method of consistent deformation method in case of prop cantilever. So, in our next class we will solve another kind of method or with more number of redundant force. Thank you.